Okay, welcome back. So, we are in the middle of the discussion of this PDF transported PDF based approach, and we have now looked at the solution procedure starting from the governing equations, the scalar PDF approach. Now, we will continue the discussion for the velocity scalar approach. Now, this is coming back or to recap the these things, your equation system. So, these are mean scalar, and in the density weighted system, so the mean scalar are written this way. This is the flux and this is the variation of the scalar. These are quite standard equations. So, any textbook, any material that you can look at, you will find this set of equations. So, I am not going into term by term of this particular equation as such, because these are absolutely standard set of equations that is available in any standard textbook. What is important, we will move to the discussion of the now velocity composition space. So, this is our physical space where the flame is there, it is an unconfined flame, and when you come to the physical space to velocity composition space, you have all n number of scalar composition along with the velocity components. So, they will form this sample space where we try to find out the probability to have certain composition and velocity of the information. So, this is again then one point statistical calculation or analysis where we try to see the from the probabilistic approximation or distribution, we try to see the that information availability. So, one point probability density function, this is how we define the joint velocity scalar PDF, where you have the velocity component and the scalar. So, this is how you define the PDF function. Now, if the PDF function, if you look at, that is the probability of finding this velocity component between these limits and the scalar composition between the limit. Now, we can get back the pure velocity PDF. If we integrate this over the sample space, we will get back the, this is joint PDF from which we can get back the velocity PDF, and this is the joint PDF. If we integrate over scale velocity space, we can get the scalar or composition PDF. And as we mentioned earlier, that case of stationary combustion system, the PDF is time independent. Now, once we look at this joint PDF, we can see these different components like after Reynolds averaging. So, there would be mean, there could be covariance and all this. So, the mean quantity we can find out, this is the mean which is within the bracket like this. This is integration of the velocity of velocity PDF over the velocity space. So, that will give me, this is essentially as we have seen earlier, the n equals to 1, this is nth moment but 1. Covariance where n is 2, so that is the difference of two velocity component and the integration of this PDF function over the velocity space. So, that is how you get the mean and covariance, and these are the terms which would be required to close some of these unclosed term arise in the equation. Now, once you do Fabre average, this is the Fabre average mean. So, then we will take the Fabre average PDF function. Similarly, for covariance we take the Fabre average PDF function, where the Fabre average PDF function is defined as rho psi by rho to u psi d psi. So, this is how you get to this thing. Now, we can also define the mass density function, where instead of having a probability to have certain values of velocity and scalar, we now consider that probability to have certain mass with the values. So, now velocity scalar mass density function, which will be defined f u phi, which is on velocity and scalar, is rho bar, and so the equation of this MDF would be also the similar transport equation for the PDF. Now, when you come to the exact equation of this mean properties, which contains the unclosed terms, this is again density averaged quantities. So, this is the term Reynolds test term which is unclosed, turbulent scalar flux is unclosed, and source term, and we will now close them using our concept of this velocity scalar PDF. So, the term which you get, the Reynolds stress term, now instead of using any Rand's equation or K or epsilon equation, now we actually close them using the information of our velocity PDF. So, that means when you have that PDF distribution function, using that, this is our, you think about, this is the covariance that we have already discussed. Then the turbulent scalar flux, we use the velocity scalar PDF to close this turbulent scalar flux. So, we do not use any information or gradient assumption or something like that to close that term. And finally, the source term, as usual, we will close using the scalar PDF. Now, if you look at the expectation value of any quantity R, so this is density average R, the expectation value would be 1 by rho R condition at V and psi with respect to velocity scalar PDF. Now, if we rewrite that, this would be 1 by rho, you take this rho psi outside, and the R is conditioned on V and psi with respect to velocity composition PDF. And this velocity composition PDF, the density average is like that. So, that means this R boils down to R condition at V psi, this is my density or fabric a mass density function and dV and d psi. So, this is where the density weighting helps to find out that expectation value at conditions at V and psi. So, this will give you an example. Now, the reason is that why we want to see how one can estimate that expected value, then we can use that. Now, this is a transport equation for the joint velocity scalar PDF. Here, this is the term, this is convection, this is the another term, this is source term, this is the term on the right hand side. Now, if you look at it, the term here on the left hand side, the chemical source term, that is in closed form. So, that is one of the advantage of the joint PDF equation or the PDF transport equation, because chemical source term which actually incurs lot of stiffness in the system, so that is in closed form, and then the convective transport is also in the closed form. So, these two terms are also in the closed form. So, this term in the right hand side is the acceleration term, which is also basically this particular term is the micromixing term, and here there is a fluctuation of pressure and stress gradient which is also unclosed. So, this is unclosed, this guy is unclosed. So, there are two terms, but this is in the, this is a gradient of pressure. So, this remains closed, but component of that which is a fluctuation of pressure and stress gradient, they remain unclosed in the system. So, one has to handle that properly to close these terms. And now, if you immediately try to see the difference between your scalar PDF and the velocity scalar PDF, the governing equation, starting from the governing equations, it becomes little bit involved or more rigorous in that sense, because as long as you had only scalar PDF, you never had this term which is arising on the right hand side. So, the solution procedure, it would be in the similar fashion. So, you need hybrid approach, that means you will solve some of the mean quantities in the Eulerian framework, then each computational framework which have some n number of particles. These particles are going to have some mass, they are not massless particle, and they will also exposed to the reaction, mixing and the turbulent fluctuation. So, they will change their position randomly, they will be affected due to mixing and reaction and diffusion. So, all sort of things would happen to this particle field, and finally, there would be a conservation of the global mass for each of these computational cell, and the information would be passed back to the Eulerian framework. So, there is a handshaking which will be required between your two framework, that is, one is the Eulerian, the other one is the Lagrangian. Then this information which will obtain from the particle properties, they will provide the closure form of the unclosed term in the PDF equation. Now, when you look at the mass density function by particles for velocity scalar PDF, it's a, you have some notional particles, in number of notional particles there would be there in each cell. So, they are having certain mass, they will be at a position, there will be some velocity and there would be some scalar. Now, previously when we looked at the scalar PDF, this is the one component or one term which was not required there, because it is only scalar PDF that we are discussing, and any velocity statistics was not available, or the information related to velocity statistics was not available from the scalar PDF. But here we have a joint velocity PDF and velocity and scalar PDF. So, the statistics of the velocity field is available. So, that is why this for the particle will also become important. Then when you look at the mean fields, we total number of per cell, the mean velocity component, mean scalar component and the mass. So, these are the important parameters that one has to satisfy to keep it or make the cognizance between the Eulerian framework and the particle framework. So, there is a simple interpolation which are used for averaging and all this. One can use some more complicated interpolation. Now, we will quickly look at how the things would, the particles would actually react to different kind of phenomena. So, there will be convection. So, the particle will move, change its position, time. There is mean pressure gradient and mean viscous stresses. For that, they will be exposed to also different stress component and all this. There is a fluctuating pressure gradient and viscous stress. So, that will allow the particle to show different kind of behavior. Then obviously, there will be mixing and then reaction. So, they will sort of react to all these different phenomena which will be occurring in the particle framework. Now, the model equation for change of particle properties. First thing, there would be a convection of the particles. So, then the displacement can be estimated for individual particle like the ui into dt. Then we can have the acceleration part which is partially exact and partially modeled. The general form of that change of the velocity would be because of the drift and the diffusion. So, this is the Wiener process. So, this process is completely stochastic, and this drift can be estimated also different stochastic model. Now, there are model equations which are often used for acceleration. Now, one is the simplified Langevin model, which uses this dui star is like, and this is some model coefficient, this is omega. Omega is nothing but turbulent frequency, and there is a difference of the instantaneous and mean velocity, and then there is a isotropic diffusion due to. So, this drift here which is calculated, this is a linear drift to the local mean. So, that means that is why this is known as simplified Langevin model, and this C naught here which is a Kolmogorov constant, which we will explain little later. And but then there is another model which is a generalized Langevin model. How it calculates this drift, that this is an diffusion which is a Wiener process, then it has a pressure gradient and shear stress gradient, and then there is a process. So, this function g is a local properties mean velocity, velocity gradient and stress and dissipation rate. And how would that look like? Now, the idea or ideology behind that is that the stochastic term represents the characteristics of the acceleration depending on the dissipation rate only. So, that means it is in inertial range of turbulence, and which is now if you change of velocity from the fluid element, this is from Lagrangian point of view, this would be ui at t plus s at uit. Now, the Lagrangian function of the inertial scales would be delta ui, delta uj will be ui this, and this is the which is approximated as C naught epsilon s delta ij. So, this is an universal constant which will be 2.1. Now, similarly, the velocity increment due to Langevin model nicely correlate with this concept, and this is where you get this term and the other part, and this particular part is correlated like this, and this is the, so this is in the sort of in your inertial range. So, that this is coming from actually the stochastic physics, where you try to see the consistency between your other phenomena. Now, Gij, which is another important term sitting there, which will reflect the properties of the turbulent field depending on the large scale of turbulence. So, that means if you go back here, this will actually depend on the large scale and which are non-uniform. So, now if you look at the choice, it is an corresponding choice of model the Reynolds stress equation, where the individual stress term is looking like this. These are production term, these are the term, and this is the term which comes from the pressure strain correlation, and this is the dissipation. So, one can actually look at this is Reynolds stress model in Rand's framework, where they can look at how these terms and then make a choice which will make a corresponds with the. Now, further there would be combination of Langevin model and Micro-Mixin model. So, that will close down the transport equation for the scalar flux. Now, if you look at the scalar flux, this is how you get, and this is the term which will appear in the closure of that, and this is the theta alpha. So, that is how you close this term, and then you go to the solution approach, which is again in the hybrid framework. That means you have Eulerian sum model, where you solve mean flow fields in the Eulerian framework, and then you go to the Lagrangian sum model, where you solve the particles. So, here you solve for mean velocity, pressure, stress, turbulent dissipation, and this mean information you pass to the Lagrangians, where you solve for position, velocity, composition with the impact of reaction and micro-mixing. So, by doing that, what you do that, then you obviously look at the global parameters like mass conservation, density, and the particles when it is crossing out of the boundary or it gets into a different bound cell. So, all these they are doing that. So, there is a constant exchange of information between two frameworks. So, that is what it does. Now, the Langevin model, if you look at the fluctuating part of the velocity, where the mean velocity is determined in the Eulerian framework, but the particle framework, when you look at there, the change of velocity of the particles is due to mean field and then this moles component, where the change is approximated like the velocity gradient, flux and the acceleration term, which is closed by the Langevin model or generalized Langevin model, like that. So, that is where you get these positions and the velocity of the particles. So, if you put up the whole set of discussion on this scalar PDF or transported PDF in one particular these things, then you can get, this is our velocity scalar PDF, this is both velocity joint scalar PDF and this is scalar PDF. So, from joint scalar PDF you can still achieve your velocity PDF and also scalar PDF. And the other term, you have time scale, you have micromixing, time scale ratio, pressure fluctuation gradient. Now, when you look at the velocity PDF, using the velocities PDF, you close the Reynolds stress term, and also you have pressure strain correlation and triple correlation, that is closed using this velocity PDF, and this is where mean velocity and mean scalar you get from the Eulerian framework. Now, using your joint scalar PDF, turbulent scalar flux and velocity source correlation and the triple correlation. So, these are the terms which you close using the information of the joint velocity scalar PDF, and only using the scalar PDF you close the mean source term. So, that will give you an idea that which one is used to close which of these terms, and these are the terms which will, these are your essentially set of terms which will arise in your, these are unclosed and you close through this Lagrangian transport approach or the Polarity density function approach. Now, one more thing which remains there is the micromixing model. When you looked at the scalar PDF, only thing that we talked about is the IEM, which is essentially every particle tries to go towards the mean. This is one of the mixing model that was available. Then there are two other model, one is called the coalition dispersion or CD or modified CD, they are available, where if this is the scalar and this direction is another scalar, the particles mix randomly in pairs. This is how the mixing model works. So, this is another model which is also often available, but it depends on the flow field. One can look at the impact of this different kind of mixing model or their impact on the I would say on the results and all these things, but that requires quite a bit of, and the one which is quite advanced and accurate is EMST, which is called Euclidean minimal spanning tree, where what it does, this particular micromixing model, the particles actually try to mix with its immediate neighbor in the composition space, and then when this mix with the neighbor, they will mix with this neighbor, that's way they form a, and that's why it's called the Euclidean spanning tree or minimal spanning tree. So, they try to look at the immediate neighbor and try to pair with it, which and then forms this tree, where in a larger sense that helps to find out the mixing model constant. This guy is one of the, when you compare these three particular mixing models, this is quite handy, or I would say accurate compared to other two. Now obviously when you say accurate, still that is that remains bit relative, because when you have a particular problem or you deal with a different kind of problems, they differ slightly. So depending on the problem to problem, you have to decide upon that. Now if I just quickly put together the strength and weakness of these micromixing models. So there are IEM, CD and EMST. First point is inner scalar PDF relaxes to a Gaussian. So this is happen in EMST only. Then all scalar remain in the allowable region, that is true for all of them. Now the conserved linear combinations are maintained, that is maintained in these two, not here. Mixing is local in composition space, which is actually true for EMST. The other thing is that the standard model for this mixing frequency does not take into account the dependence of mixing rate on scalar length scale and dependence of mixing rate on Reynolds number, Damn-Coulomb number and Smith number effect. So these are very important effect which can be also or need to be looked at. So just to sum up the things for the velocity scalar PDF. So PDF transport equation, you have the chemical source term, which is one of the issue is that's in closed form. So that's the biggest advantage, which is true for both scalar PDF and velocity scalar PDF. Then the closure solution of the PDF equations are usually achieved in the particle method. So the framework, essentially one call it a hybrid method, which has both the Eulerian framework and the Lagrangian framework, which is numerically quite robust and convenient for use in combination with the finite volume methods or the codes. Then in scalar PDF you have random walk model and micromixing model needed, whereas in velocity scalar PDF you require Langeville model and micromixing model. So that will close the term which are there in unclosed in the system. Just to end this discussion with a simple example, you can see this model with a LES of turbulent jet flame. This was done long time back in 2007. This is an Sandia flame D, where joint scalar PDF was solved, which is computed through filtered enthalpy equation, chemical mechanism. So the stochastic differential equations are position and in the component, where you can see this structure of the D, E and A, where these are instantaneous structure, how it looks, and there are mean values also which was compared. You can go to that reference and find out the rest of the detail. This is just to show you how that thing actually worked, and one can find out also the mean from the scatter plot. So that's we stop the, or essentially that concludes the discussion on the transport PDF method, and we will stop the discussion today here, continue in the next lecture.